Okay, friends, welcome to lecture number 15. This is week 3. So, at the end of every week, as I said, we are going to discuss some tutorial problems. So, in this, this is mostly focusing on the tutorial. So, in this lecture, whatever we covered in this week, so we are going to pick some of the problems and solve it. So, here before even going to some problems, so we need to know, I mean if you see the previous previous lecture, the water measuring devices. So, you clearly see some head differences, right. So, that difference is basically it could be due to the friction loss or some other bands or what are some obstructions. Okay. So, those things. So, if you notice those differences, so how to estimate that head differences basically mostly the head due to friction or head due to entrance losses or head due to bands or head due to expansion or contraction. So, those things. So, before going to some tutorial problems, so let's see here. So, energy loss basically if you see so major energy loss could be due to the friction. Okay. So, for friction we have two equations, one is Darcy-Weisbach equation. So, this is capital W. So, Darcy-Weisbach equation and Chase's formula. So, these two can be used to find out the head loss. So, head loss according to the Darcy-Weisbach formula 4 F L V square by 2 Z D. Okay. So, where F is coefficient of friction, that is 16 by R E, where R E is Reynolds number, which is less than 2000. So, F is equal 16 by R E. So, mostly this is a viscous flow, whereas if it is more than 2000, R E is more than 2000, sorry, from more than 2000 or from 4000 to 10 power 6, 0.079 by R E power 1 by 4. So, where R E is estimated as V into D by mu, mu is the kinematic viscosity, diameter of the pipe, V is the mean velocity. So, Chase's formula if you see, V the velocity is equal C into square root of m I. So, whereas m is A by P, okay, so that is hydraulic radius, and I is equal to H f by L. So, where H f is here. So, you are going to estimate H f here, okay, by L. So, the terms are defined here. So, you can go through this. So, C is the Chase's constant and I is the loss of head per unit length of pipe. So, that is H f by L. Okay. So, with these two equations we are going to find out the head loss due to friction. Okay. And then, so there are some minor head losses that is due to sudden expansion of the pipe. Okay. So, that is V 1 minus V 2 whole square by 2 Z. So, V 1 V 2 that is suppose you have a pipe, right. So, sudden expansion. So, you have a pipe like this. So, here let us say V 1 and here at this point V 2. So, V 1 minus V 2 square by 2 Z will give the head loss, sudden expansion of head loss due to sudden expansion. Similarly, sudden contraction of the pipe, okay, and entrance of the pipe or exit of the pipe, or you have a obstruction and bend in a pipe. Okay. So, these equations can be used to find out the minor head losses, right. So, you can also get these minor head losses using the table, which will be discussed in I think the pumps tube belt section. Okay. So, we are going to discuss that in a way. Okay. So, so there what will happen for a there is a nomograph. Okay. So, for a particular shape or particular bend type or or for example, you are talking about the pumps. Okay. So, at the bottom you have strainer, okay, and then bend and then valve. So, for each thing in nomograph you get the equivalent pipe length. Okay. So, and then you go back to the table, the friction table, and then for that particular length, find out the friction head loss for 100 meter. Okay. That will, the table will give 100 meter, and then you can reduce it to the particular length of the pipe. Okay. So, that is the way of calculating the mining head loss from the nomograph and friction table. And then, so now, okay, so let us do an example based on the energy of pipe flow. So, friction head losses. So, here basically in this example, the find out the head loss due to friction in a pipe. Diameter is given and the length of the pipe is given, through which water is flowing in a velocity 3 meter per second. So, asking use Darcy's formula and Chase's formula, for which C equal to 60, that is Chase's coefficient, and take kinematic viscosity mu 0.01 Stokes. Okay. So, the solution here is, so let us summarize the inputs, that is a D 300 mm. So, convert that into meters, and length 50 meter, V 3 meter per second, C change is constant 60, and kinematic viscosity is 0.01 Stokes, and then if you convert that into meter square second, 0.01 10 power minus 4. So, Darcy and Weisbach equation, so HF is 4 FL V square by 2 ZD, and for this, so R E is equal to V D into, this is a mu, the kinematic viscosity, and put that, and you get R E is equal to 9 10 power 5. So, you are going to use the second equation F, that is F is equal to 0.079 into R E power 1 by 4, and you get this friction factor, which is 0.00256, that F, and I think the remaining things all are given except F. So, F we got it, and you can substitute D, G, V, L, and you get HF. Okay. So, that if you see in the next slide, so HF, you substitute all the values. So, this is the value of the friction head loss using Darcy-Weisbach equation. And similarly, the Chase's formula, V is equal to C into square root of m I. So, V is given and C is given. So, m d by 4, so which is also given, whereas I, so whereas 3 is equal to, that is velocity 3 is equal to 60, this C into square root of 0.075 into I. Okay. So, from here I is equal to, you got 0.0333, and I, you have equation HF by L. Okay. So, L is given. So, find out HF, that is 1.665. So, this way you can use both the Darcy-Weisbach equation and Chase's equation for finding out the hydraulic head, friction head. Oops. Okay. So, and the next exercise is because in this week we introduced the open channel measuring devices, isn't it. So, here a rectangular channel having a bed slope of 0.05% and Manning's roughness coefficient of 0.01 carries a discharge of 5 meter cube per second. If the channel is designed the most economical section, if you remember the most economical section, that is equal, so your what is the depth is equal to B by 2, right, depth is equal to B by 2. Okay. So, economical section, so the width of the channel in meter will be, so find out what is the width of the section. So, this is a rectangular, this is the B, and this is the D. Okay. So, now you have to find out what is the B value. So, summarize the given values. S equal to 0.05, you convert that into 5 into 10 power minus 4, Manning's n is given, and Q 5 meter cube per second. So, area in case of rectangular channel, that is a B into D, and put that in, the Manning's equation V is equal to 1 by n into A by P into 2 by 3 S power 1 by 2. Now, Q is equal to A into V, here Q is equal to A into V. So, where A is B into D and V is 1 by n 1 by n into, so A B D into 2 D plus B. So, this is perimeter. Perimeter means from this point plus this plus this plus this. So, D plus B plus D, okay, 2 D plus B, 2 by 3 into S power half. Okay. So, the next the most economical channel section D equal to B by 2. So, substitute B by 2 for D. Okay. So, then what happened? So, wherever the D, just substitute it to B by 2, and then Q is given 5, and then simplify this, and n value is given. Okay. So, an S value is given. So, substitute all the values and you will end up with B 8 by 3, and finally, the B is equal to 2.48. Okay. Okay. So, that is example, this is exercise 3.3. The next, so in this example, this is straightforward example. Okay. So, a steady discharge of 60 meter cube per second is passing through a trapezoidal irrigation channel with a bottom width of 5 meter. Okay, bottom width 5 meter. This is the trapezoidal section, the 5 meter bottom width, and bed slope of 0.05% and Manning's roughness coefficient 0.025, and the conveyance of the channel in meter cube per second is. So, the question is, what is the conveyance of the channel? So, the conveyance of the channel is equal to the area into 1 by n into r power 2 by 3. So, this is called conveyance. So, you have to find out what is this conveyance, that is K. So, given values are Q is equal to 60 meter cube per second, SF 0.05. So, that will be 0.0001, and since Q is equal to A into V, right. So, you put the Manning's equation for velocity and K into S for 1 by 2, where K is equal to this conveyance. So, Q is equal to K into square root of SF, and now you can easily find out K. So, that is 6000 meter cube per second. Okay. So, and the next exercise, that is a tracer example. Okay. So, initially the tracer 50 gram per liter solution of tracer was discharged into a stream. So, this is a stream going on, right. So, here initially, so this is a C1 which is 50 gram per liter. So, that is the concentration of the tracer which is been released to the stream, right. So, this has a discharge rate of 20 ml per second. Okay. Discharge constant 20 ml per second at downstream section. So, at downstream section, this is upstream and downstream section, the tracer was completely mixed and attained equilibrium. So, at this, let us say at this point it attained an equilibrium, and the concentration. So, here the C2 has concentration of 10 ppb, okay, 10 ppb. So, assume the background concentration is 0. So, here Cb, which is background concentration, is 0. The stream discharge is. So, what would be the stream discharge here? So, this is the problem. Okay. So, given the C1 is given and C2 is given the 10 ppb. So, C2 10 ppb, which is equal to 10 into 10 power minus 3 ppm, or 10 into 10 power minus 3, this is milligram per liter, right. And then C2 is 10 ppb, that is fine. And then so here yeah, the same thing, 10 into 10 power minus 3 milligram per liter, or 10 into 10 power minus 3 into 10 power minus 3 gram per liter, right. So, then this will be 10 power minus 5 gram per liter. So, that is the same as this, okay. And Q is equal to 20 ml per second. So, this is 20 into 10 power minus 6 meter cube per second. So, if you can recall the equation for Q, right. So, the Q is equal to Q into C2 minus C1 divided by C2. So, let us see the next slide. We have yeah, C2 minus Cb, okay. So, if you see, this is a Q naught, which is equal to Q into C1 minus C2 by C2 minus Cb. So, substitute these values, and Q naught is equal to 99.99 meter cube per second. Okay. So, let us go to the next example. So, in this exercise, this is straightforward. If you see, the discharge through a 90-degree V notch channel. So, there is a V notch, this 90-degree V notch, okay. So, theta is 90. There is a head of 0.5 meter and coefficient of discharge of 0.6. So, find out the discharge. So, this is a triangular notch. So, you can directly get the equation, triangular notch equation, and substitute the values here. So, CD is given 0.6, 8 by 15, G, so tan 90 by 2, and this. So, you can directly substitute the values and get the Q is equal to 0.25 meter cube per second. Okay. So, this is another example, which is a trapezoidal channel of 0.5 meter bottom width and 1:1 side slope and carrying water at a depth of 0.4 meter. If the channel slope is 1 in 400 and roughness coefficient is 0.02. So, and find the mean velocity. Okay. So, this is the thing. So, in this, so since it is a trapezoidal channel, so B is given, so 0.5, this is bottom width, and Z 1:1 and D 0.4, this is depth, and N 0.0 Manning's roughness coefficient. So, S is equal to 1 by 400. So, just that is a 2.5 into 10 power minus 3. So, find out what is Vm. Okay. So, here T is equal to B plus 2D, because this is a trapezoidal. So, the top width, which is equal to B plus 2D. So, why B yeah, this is a 0.5 and 2 into D 0.8. So, D is given. So, B, so D is given and B is 0.5, okay, this is small b anyway, and top width 1.3 meter, and A is equal to 1 by half D into B plus D plus B plus 2D. Okay. So, now A, if you substitute the values, you get 0.36 meter square. So, the next is P, wetted perimeter. So, that is B plus square root of 2D, and substitute these values, you get wetted parameters 1.63 and 1.2. Hydraulic radius R is equal to A by P. Okay. So, that will be 0.221, and minimum velocity V min, that is 1 by you can use Manning's roughness Manning's equation, and substitute R value, S value here, and you get the velocity, that is 0.9 meter per second. Okay. So, these are some of the examples which are given in the competitive examination like GATE. So, you can also try a few more examples in other textbooks I mentioned in as a reference books. Okay, so basically in this tutorial we focused the exam questions which are basically on the basis of the water measuring structures. Okay. And then initially we started with some head losses, the friction head losses, and how to estimate there is a major friction major head loss, and how to estimate minor head losses, like you have bends, you have some structures like enlargement, exit, all those things. So, yeah, so I think we will move forward to the next lecture. So, that will be on water application methods. So, in that we will be focusing on surface irrigation methods, okay, sprinkler, drip irrigation, and those the basic principles, and then design principles and the workload examples in the next coming in the 2 weeks. Okay. Thank you so much.